answers to your homework. It really wasn't much of a homework. It was just, hey, here's the vocab for the new unit. You go and see if you can find these words by yourself. But here's the answers to your angle terms notes, which was on the calendar for Friday. There are 4 ways to name an angle. There's probably more, but in this picture, for this angle, there's 4 different unique ways that we could name this angle, okay? So, oh, good point. You said acute. Now be careful. Acute is classifying an angle. We're going to learn how to name an angle. So just like if someone came up to me and said, oh, you're a woman. That's not my name, right? That's my classification. I'm either male or female. I'm female. But my name is Mrs. Tanton. So my classification is female, but my name is Mrs. Tanton. So yes, that's an acute angle, although we don't know the measure of it, so be careful on that. It's an acute angle, but there's 4 ways to name it. I can name it angle Y. Oh, good. You're putting them in the chat. Okay. Why would I choose angle Y? Why would I not call it angle X? What is Y called? It's a part of the angle. The vertex. Very good. So you can name an angle using its vertex. Sometimes you can name an angle using its vertex. We'll talk about when you can. We can also call this angle 1. We can call this angle XYZ. And we can call this angle ZYX. What do you notice about 3 and 4? What do those have in common? Vertice. Vertice is the plural of vertex. Okay. What do they have in common? Good, Chloe. The vertex is in the middle. So when you name an angle with 3 letters, just make sure the vertex is always in the middle. You're going to go in order. The vertex is in the middle. Okay. So this is old news. Old news. An acute angle is less than 90. Is it less than or equal to 90? No, less than 90. A right angle is exactly 90, and we put this symbol right here to show that it's 90. An obtuse angle is less than 180, but greater than 90. We're not going to deal with angles greater than 180 in this class. They exist. They're called reflex angles, but we're not going to use any angles greater than 180 in this class. Did you learn this in 2nd grade? Oh no. And then a straight angle is exactly 180. Okay, I'm boring you. All right. This is one of the words that was possibly new to you. What is the relationship between angle 1 and angle 3? So if you turn your head sideways, hopefully it looks like the letter V and then the letter V, like back to back, the letter V. So the relationship between angle 1 and angle 3 is that they are vertical angles. They're opposite each other. Their position is opposite, not the measure of the angle, the position. So angle 1 and angle 3 are called vertical angles. And there's something that's always, always, always true about vertical angles. Watch this. If I take angle 1 and I rotate it, and then I put it right there, what did I just prove with the smartboard? It's not a formal proof, but what did I prove with the smartboard? Yeah! Angle 1 and angle 3 are congruent. They're the same measure. So vertical angles, we're going to learn, are always congruent. Okay, what about angle 2? What about angle 2 and angle 4? Do you think they're congruent? All right, let's take this one. Let's rotate it. Dun, da, da, da. Angle 2 and angle 4 are also congruent because they are also vertical angles. Yes. So we just proved that vertical angles are congruent. So find where you wrote vertical angles on your vocab, and I want you to write always congruent. Every time. Every single time they're congruent. So if angle 3 is 80 degrees, then angle 1 is 80 degrees. If angle 2 is 100 degrees, then angle 4 is 100 degrees. Vertical angles are congruent. Every time. Yes. Okay. Adjacent angles, another one that might be new for you. When you see the word adjacent, I want you to think next to. And people use this word in the real world. They use it for things other than just angles. You might be sitting adjacent to someone. That means you're sitting right next to them, okay? So adjacent means next to, if you want to add that to your notes. And adjacent angles are not necessarily congruent. They can be two totally different angles. They're just two angles that share a ray. Look at angle 1. Angle 1 is all of this space in here. That's angle 1. Angle 2 is all of this space in here. The only thing that they share is this ray right here. So to be adjacent, they have to share a ray. Now let me draw an additional picture just to make sure we know what adjacent is and what adjacent isn't. Angle 1 and angle 3. Those are like kind of next to each other, but wait, there's someone in their way. Angle 2 is in their way. So angle 1 and angle 3 are not adjacent. They have to share a ray. What's the only thing angle 1 and angle 3 share? They share a vertex, but they're not adjacent because they don't share a ray. Okay? So just make sure that they have a common vertex and a common side. And that would be that ray that they're sharing. Okay? It's not really a segment, it's a ray, because actually the definition of an angle is two rays that meet at a common point. So an angle is made up of rays, so that's why I said ray and not segment. Next word that might be new is linear pair. And you know what? Out of all these words, linear pair is going to show up more than any of these for the rest of the year. Linear pair. You're going to see them over and over and over, and you're going to be tired of me saying linear pair. So, linear pair is really a loaded word. There's a lot in that definition, in that word. Linear sounds like line, and there's 180 degrees in a line. And then pair implies that there are two. Very good. So what this is saying, what a linear pair is saying, is that it's two angles that add to equal 180. That their sum is 180. So two angles, angle 1 and angle 2, they have to be adjacent. They have to form a straight line. And they are also supplementary. They add to 180. So linear means line. They better form a line. And pair means there's two of them. Two angles that form a line. Let me just make sure we understand what a linear pair is and what a linear pair isn't. Graham, why are you showing the screen through your camera? Okay, ready? A linear pair is supplementary and is adjacent. Here's an example of what a linear pair doesn't look like. Those are disconnected. Are those still supplementary? Yes. But are they a linear pair? No. So I just wanted you to see the difference. That might be on a quiz. This one, supplementary and adjacent, the linear pair, and the other one, supplementary but not adjacent, not next to. Those aren't next to each other. Okay. Before we move to this one, real quick, we didn't talk about complementary and supplementary because I assumed that was prior knowledge for you. But just to give you a quick reminder of how you can remember the difference, because people get them mixed up. One adds to 180 and one adds to 90, and sometimes it gets confusing. So you've probably seen this before, but the way that you can remember is you can take the C and you can put a stem on it. And look, the C turns into 90 degrees. Do you see the 9? 90 degrees. So complementary adds up to 90. And then the S, you can turn it into an 8, and then there's your 180 degrees. So the C turns into a 9, and the S turns into an 8. So hopefully from now on you won't ever get them mixed up. Okay. Let's see if you can draw this figure. I'm going to give you a lengthy description of a figure that includes angles, and I want to see if you can draw it. So go ahead and take a minute to do that. Anyways, okay, so did we draw a picture? First of all, these two angles form a linear pair. So I'm going to start by drawing a line. Okay? We've got ABC and DBC. So you kind of just have to play with it. We know B is the vertex, right? Because that's the middle one and the middle one. So one of these is called ABC, and one of them is called DBC. But I'm not sure. I might have to adjust my picture. We're just playing with it. Point E is in the interior of DBC, so E is somewhere in here, and DBE is obtuse. In my picture, is DBE obtuse? Oh my goodness, not even close. But now I know exactly what to do. I know that now C needs to go over here because I need room. And then E can go anywhere over here as long as it's past 90. And now I think I have the right situation. Are they a linear pair? Check. Is point E in the interior of DBC? Check. Is DBE, is that angle obtuse? Check. So good. Yours should have looked a little bit like that. True, false, or cannot determine. Some of my angle symbols were kind of falling down there. Sorry about that. All right, let's go through this and see if we can determine. Now, it takes a while to get used to. When I use 3 letters, which angle am I actually talking about? Stop typing. So make sure if you're having trouble, you're following it with your finger, okay, as you read. V, W, U. Start at V, go to W, and end at U. V, W, U, and U, W, T, I'll get a different color, are complementary. True, false, or cannot determine. Cannot determine. And actually we haven't done the assumptions part of the lesson yet. That comes next. So hopefully after I teach you the assumptions, you'll be like, oh, we cannot determine if they're complementary because we don't know what the measure of that angle is. What if that picture just isn't drawn perfectly, but that really is a 90-degree angle? What if I told you that this one was 50 and this one was 40? Then they would be complementary even though it doesn't look like it's complementary. So you can't trust your eyes. You can only trust the data. You can only trust the numbers. So this one we would not be able to say because no one told us what the degrees of those angles are. Okay? Right. Oh, not drawn to scale just means 90 doesn't really look 90. I'm just saying what everyone else says. Okay. All right, let's try the next one. RWS and SWT equals RWT. Part plus part equals, is that the whole? Did I name the part and then the part and then the whole? Did I do it correctly? Yes. So on this one, we don't care if it's drawn to scale. This has nothing to do with the scale. This has to do with if this angle is adjacent to this angle, then together they form the whole angle. So that one's true. Next one. RWS, same one, and TWV are vertical angles. They're vertical angles. So maybe I didn't teach vertical angles very well because it actually is false, but see, I'm glad we're talking about this. Those angles do share a vertex. I agree. I agree that they share a vertex, okay? But vertical angles are formed when you have the letter X. If you don't have the letter X, like as in a line intersecting a line, you can't get vertical angles. Angle 1 and angle 2 are vertical. Angle 3 and angle 4 are not vertical. Do you see how that is not formed by the letter X? Those are like a straight line and then a V. And those are not vertical angles. Do you see the difference between my two pictures? Because that comes up a lot. 1 and 2 are vertical. The X's, those are not vertical angles. They're different. Okay. Glad we went over that. We're gonna keep going. We're not gonna talk about those next two. Next one. So it has to look like intersecting lines, but the angles opposite have to be, yes. Not even just look like intersecting lines, it has to be intersecting lines. Yes. What is the truth value of the following statement? The sum of two acute angles is also an acute angle. So remember, truth value means is it true or is it false? And if it is false, there better be a counterexample. You better have one ready to go. Very good. You got it. It is definitely false, and there are a million counterexamples out there. Some of you said, oh, I can add two acute angles, and I can get a right angle. Or some of you said, I can add two acute angles. Those are both acute, and I could get an obtuse angle. So, we're just trying to bring reasoning back into it to make sure you don't forget how to do reasoning. All right. A protractor, haha, get it? It's like a tractor. Protractor measures angles, right? Haha. Okay. We're not getting protractors out today. We will use them another day, but not today. But I wanted to remind you how to use one just so that your memory is jogged, okay? To use a protractor, the key is to get this middle, the bullseye, on the vertex of the angle. And then you simply start at 0, because this is when the angle's 0, and you just read your numbers. So if I start at 0, 10, 20, 30, 40, and I'm a little past the 45 mark, so I'd call it either 46 or 47. Okay? If your angle is obtuse, you still put the bullseye on the vertex. You still start at 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, and we're probably at about 114 there. We're a little bit before the 5. Yes, I'll warn you before you need it. I need to look at the calendar and see what day you need it. Okay, here's the second part of the lesson. Today's lesson, part 2. It is what can you assume and what can you not assume from a diagram. And I think we definitely need to have this discussion. What may be assumed is less enlightening than what may not be assumed. So we're going to pay more attention to what we can't assume, but let's just go over what we can assume. We can assume that if a line looks straight, that it is straight. So there's no saying, ooh, that's almost, what if that's 179 degrees and not 180? No, you're allowed, if it looks straight, you are allowed to assume that it's a straight line. That's allowed. Collinearity of points. That just means that if Miss Tanton puts dots on this line, you don't have to wonder, is she trying to trick me? Is A like right below the line but not perfectly on the line? No, I'm not trying to trick you. You are allowed to assume that if it looks like it's on the line, it is on the line. Those are collinear if they look collinear. Intersection of lines. If you see two lines crossing, it's not a figment of your imagination. They really are crossing. Now, you can't assume they're crossing at 90 degrees, but if they look like they cross, I'm not trying to trick you. There's not one in front of the page and one behind the page, like this. Anyways, if they look like they cross, they really do cross. Relative locations. We were talking earlier, let me make that a capital since it's a point. Oh, that just made it worse. We were talking earlier about being in the interior of an angle. If I say B, if I draw point B and it looks like it's inside the angle, you can assume it really is inside that angle. It's not somewhere else. And then adjacency of angles. You can assume that angle 1 and angle 2 are adjacent. You can assume. And then I love the last one. That's the best one. The figures that are drawn on your paper, you're allowed to assume they exist. Isn't that funny? You're allowed to assume the existence of the figures. They're not a figment of your imagination. They really are there. Okay, like I said, that's not as enlightening as this one is. And we're going to talk about this one. What you are not allowed to assume. Are you ready? Okay. Congruence. We went over this a little bit. I cannot assume that AB is a congruent to BC just because they look congruent. I cannot assume. The same goes with angles. I cannot assume that angle 1 and angle 2 are congruent just because they look congruent. All right, midpoint. Yep, B sure does look like the midpoint. But if there are no tick marks on your picture and the directions don't say it's the midpoint, you can't assume it's the midpoint. I skipped over this one right here. Relative size of segments and angles. In that picture, which angle looks bigger? Angle 2. You're right. But you can't assume that it's bigger until you actually solve for the measure of the angle. That's what I keep saying. It could be not drawn to scale. Angle 1 really could be larger. You have to solve for it first. All right, bisector and midpoint, those go together. You can't assume those. Oh, this is my favorite one, number 5. I guarantee I'm going to give you a problem, and there's going to be something like that, and you're going to be like, oh, that's 90. Even though there's no box there. Even though there's no indication that it's 90. We never assume they're perpendicular. Even if they're drawn with a computer, and it looks perfectly straight, it looks perfectly 90. We will not assume until we solve for that angle. And then we can't assume, like, this triangle, it looks isosceles or it looks equilateral, but if you don't know the measurement, you can't assume. And then last one, non-intersecting lines. I give you 2 lines, and this was actually on your test, if you remember. Those sure do look parallel. They sure do. But if I don't have a marking on them, if I don't have those little arrows that show that they're parallel, then we can't assume they're parallel. Okay. To assume or not to assume, that is the question. So you should have this sheet out in front of you. Hopefully. And I want you to go through all 15 statements and decide if you can assume or not assume. So I'm going to give you a little bit of time to decide if you can assume or not assume. All right, let's go over the answers. I hope they're the right answers. Here are the ones that we may assume. See how you did and ask me questions on the ones you got wrong. Out of 15 statements, you can only assume 5 of them. Number 5 said that one of those angles is obtuse. But if you look at your sheet, things that may not be assumed is relative size of segments and angles. So if we don't know its measure, then we can't say it's obtuse even though it looks obtuse. Number 7, they don't intersect. I agree that those look parallel. I agree. But what if one of them is slightly angled towards the other one? It may intersect later in the diagram. Like if this one has a slightly different slope, later on they might end up intersecting if they're getting closer to each other as you go. They might. We don't know because no one told us they were parallel and no one put any symbols to say they were parallel.